Here we have a fun circular motion problem where we have some kids playing around on a merry-go-round. And as we can all imagine, you get one kid pushing really fast and everybody gets this sense they're getting thrown off of the ride. As we understand with circular motion, really that is the inertia that gives that centrifugal force feeling of being thrown away. What really needs to happen is you need a centripetal force to remain on the circle. All right, so let's draw a free body diagram to try to identify those forces. And it can be a little bit tricky with one of these ones because you got to look at it maybe a couple different ways. If we take a top view, you would have the ride, and you might have, the pull from the ride. You might have a kid hanging onto that ride onto the side. He's hanging on desperately, all right, and that thing's whirling around. We've got some velocity here. That kid's moving this way. The ride's spinning around, right, and we can identify the radius of the ride. And we have some velocity of the rider, right? And as we're spinning, you might be able to figure out the RPMs here, which is what they're looking for, right? Well, if I'm looking at a top view, really the only force you're going to see is that that kid is hanging on for dear life with some kind of applied force. And that force is going to be an inward applied force of the kid hanging on. And you might think, well, it looks like he's getting pushed away if he's that rider, but it's almost like he's hanging from a pull-up bar, right? He'd be actually pulling inward in order to stay on that ride. So his applied force has to be in order for him to remain on that ride. You can also look at this free body diagram. Again, this is a top view, right? And from the top view, you actually don't see gravity. If I look at a side view, you would have that rider, and you might think of that ride more as a disc. Try this again. And there's maybe a pole sticking up here, and you maybe have that rider, his feet on there, and he's hanging on, right? And you would see that, once again, that rider is applying a force inward, right, in towards the center. And here from the side, you would see that that rider would have some weight, and also, well, his feet are on the ground, so you might see that that rider also has an upward normal force, right? And as a result of those two forces, they cancel out. That rider is only accelerating inward, right? So again, when we look at these circular motion problems, we have to look at the path of the rider, and that rider is in a circular path. And so we have to only look at the forces that act centripetally, right? And we know that the sum of all the forces is equal to m times a. That's Newton's second law. But which way are we accelerating? Well, in this problem, we are accelerating inward. We have a centripetal acceleration. So now we look at all the forces that act centripetally that cause that mass to accelerate centripetally towards the center, right? And so what are the centripetal forces? Well, there's only one force. It is the applied force, is the centripetal force. It is the only force that points to the center of the circle. All right, before we split our forces into x and y, and if we look in x and y, Fa is in the x direction, the normal force in Fg are in the y, we'd have to treat them as separate columns, right, and they don't interact. Well, same thing here, except rather than the x direction, we're going to call the applied force a centripetally directed force. And on the right side, you would have the mass, and remember, centripetal acceleration is v squared over r. Right, so really this becomes our equation, right? And when we look at what's given in the problem, we have some things. We have the mass of the child, we have the radius of the ride, and we have the force the kid can apply. And what we want to know is the speed of the ride, right? In this case, they wanted in RPMs. They want how fast, which is really what v is. So we're going to substitute the values in here, and this is where we can put in the values from the problem. So our applied force, we're going to substitute 360 newtons because that's where we know that's the max this rider can hold on. What direction is that force? Well, on the picture it's left. In the past we'd say left is negative, but actually we're now thinking in and out because we're in circles, right? So it is facing inward, so I'm going to say it's a positive force. On the right side, I have my 20 kilograms of mass, and I have my unknown velocity over my radius of 2 meters. Right? And the units are going to end up working out here. I won't go through the whole mess. Remember, a Newton is a kilogram meter per second squared. And we're just going to solve this for v here by multiplying both sides, or rather we can simplify here. Let's 20 divided by 2 becomes 10, right? And then we can divide both sides by 10, and we find that we get 36 is equal to v squared. Well, then what is v? V would have to be the square root of 36, which is simply 6 meters per second. Right? So at 6 meters per second, anything more than that, and the child's not going to be able to hold on. It would take a greater amount of force to keep that kid moving in a circle. But hold on, they want RPMs. So let's convert 6 meters per second to RPMs, right? And remember, RPMs is just revolutions per minute. So I'm going to set up my fence post. I have 6 meters per 1 second. And let's get rid of meters. How many meters is 1 revolution? Well, 2 pi times the radius is 2 meters, is what 1 circumference is, and that is the same as 1 revolution. Right? So the units, meters, cancels with meters, and now I'm in revolutions per second, but I want revolutions per minute. So I'm going to cancel seconds, go to minutes. There are 60 seconds in 1 minute, and I can cross out my units, and I'm left with minutes in the denominator. So now I have revolutions per minute, and we can pull out our calculator and evaluate. So in my numerator, I have 6 times 60. And in the denominator, be careful with your parentheses because we want to divide by the whole denominator. 2 times pi times 2, well, that's 4 times pi, second pi. And I should get 28.6 RPMs. So my answer, 6 meters per second, is the same as 28.6 revolutions per minute. This ride would have to go around 28 times in 1 minute, at which point that speed would start to overcome what the kid can actually hold. That kid can hold 360 newtons. Anything faster would be a greater acceleration. My centripetal acceleration would increase if the velocity goes up. And since the mass is not changing, it would require greater force to maintain that circular path.